I thought I'd do today, one of the things that's come across from what I've seen so far is that there are a couple of topic areas that I think we need to take another look at. The one I'm going to hit is one from the previous piece of work, not the one you just handed in yesterday, this morning, but from sort of previous attempts, at previous questions. I think one of the areas where I just need to sort of recap with you, and it's one that seems surprising on the face of it, because the concepts are pretty simple, which is moments. It's moments and talk. So what I need to do really is, well, if you pardon the pun, talk you through the topic. In terms of the basic concepts, everybody knows the concepts. They know the idea that a moment is equal to force times distance. Now, this distance here is always a perpendicular distance. So what that means is if you've got a pivot, and you've got your lever of some description, and you've got a force. Now, if I apply a force, if I apply it at right angles, that's fine. It's just force times distance. The only time it's different, and I'm going to demonstrate this one in just a second, is if I apply a force at a funny angle. Now, there are lots of different ways of looking at this force. I'm going to today just see if it's relative to that angle, but you could use the same bit of maths and physics if you were given this angle. So this would be a force. This distance is not S because it's not perpendicular to the line of action of the force. I'm going to call this one L for now. Okay. Now, what you do is when you're looking for the force times the distance, it's the distance perpendicular to the line of action of the force. So perpendicular means right angles. So here we go. I've got a right angle here. So if I draw my line from the pivot to my line of action of the force there, actually, whoops, just get this right. I'm going to use a different color to make it easier to see. This isn't a force, this is a distance. That is the perpendicular distance. Now you can use bits of geometry here. If that's at right angles there, we know that this angle and this angle are actually the same angle. They're actually the same. If we rotated the whole triangle round, so that was 0, if we rotated that force round so that was 0, then the perpendicular distance line would be perpendicular there, so that angle would be 0 as well. So it's logical and it makes geometric sense that that angle and that angle are the same. So all I've really got to do is recognize, using geometry, what S is in terms of L and theta, and that angle, I mean. So the moment is equal to the force times, well, if I'm wanting to work out the adjacent, that's cosine, that's the cosine rule. So it's times length times the cosine of theta, okay? So if that becomes 0, then that factor becomes 1. Okay, because the cosine of 0 is 1. Now, so that's the basic concept behind what a moment is. And it's the confusion, I think. Sorry? No, no. The confusion, I think, occurs because people get really sort of bothered by this. What is this perpendicular distance? I always think of it as the line of action from the force. So here is my force here. Now, if I extend that line of action, I've actually got a particular continuous line. And the perpendicular distance is the distance from the line of action of the force to the pivot or the fulcrum. Okay? So that is something people get very confused with. And they say, well, which formula is correct? Well, actually, both of these two formulae are correct. It's just that this one is sort of an evolution of that one. And if you actually, if the force is perpendicular to the line of is perpendicular to L here, the force was down here, then actually that, as I say, basically simplifies to that. So that's the first bit of the of sort of the moments and talking. There's something people get very confused by. The other thing that people get very confused by, well, most people get the idea about equilibrium. And it is something to remember. A couple of you kind of guessed at it. If you look up equilibrium, it basically means balance. So the thing to remember, if it's balanced, in terms of the moments, it is the sum of all moments about a pivot. Whoops. Equal 0. If you want to write it completely, what you do is you'd say the sum of clockwise moments equals the sum of anti-clockwise moments. Okay, about a pivot. So really, if you want to give a very complete definition of what equilibrium is, that's your definition right there. It is the sum of all moments about a pivot equals 0, which means that the sum of clockwise moments equals the sum of anti-clockwise moments for equilibrium. It's called the principle of moments. Okay, that's the principle of moments. But the other condition for equilibrium is actually the sum of all linear forces in all directions equals 0. Okay, and that is sort of the second bit of it. And as I've said before, it's a little bit of a cheek, but the best way what's going on here? Right. The best way to tell whether or not you need to put the linear bit in, there are two ways. Way number one is if you see the question and it's worth 2 or 3 marks. If it's worth 2 or 3 marks and it says state the conditions required for equilibrium, then they probably want you to put the linear bit and the rotational equilibrium, the moments bit. Okay. Also, look at the context of the question. If you look down at the question, does the sort of the content seem to sort of hint that you might have to think about resolving linear force vectors? If it does, then you probably want to put that in as well. So it's sort of a double way of telling. But as I say, it's down to the number of marks mostly. If it's a 1-mark question, then you look at what the question's about. If the question's about linear forces, you use the linear force equilibrium definition. If it's all about rotation and balancing about a pivot or something like that, then it is all about the principle of moments. So that's the basic idea anyway. I mean, apart from that, you actually don't need to actually learn anything else. But what you probably could do with doing is being able to apply it. So the simple ideas, I mean, I'm not going to waste your time with a simple seesaw situation. Why? Because you can do that standing on your head. The bit that I think people struggle with are when you get some more complex examples. So I'm just going to go through a couple with you and just show you how you go about doing them. So imagine you've got a diving board. If you've got a diving board, there's your diver, about to jump off. Their force, their weight, is given by the mass times g. Be very careful when you look at a moments question as to whether you'll give a mass or weight. Remember, mass is the amount of matter, it's in kilograms. You've got to multiply it by 9.81 to get the force downwards, their weight in newtons. Now, if you've got a diving board, anyway, if we've got a diving board, then there are going to be two supports. There's going to be one support about here, and there will be another support tying it down about there. So what's actually happening if you're on the diving board, we could try and work out the forces involved in this diving board. So what we'd need are a few distances. So I'm going to take a few values just because it's quite handy to actually understand what these distances and what these values are. So I'm going to assume, well, the mass of a diver, if they're, I don't know, if they're a young person, they may be 50 kilograms times G would be about 500 newtons. I'm going to ignore the weight of the diving board for this because I think it's going to add complication. Now, obviously, if they're stood over here and we're exerting a force of 500 newtons, if we take the pivot here, then there must be a downwards force to create an opposite moment. So I'm going to call these supports A and B. Now there must be a force downwards from A. There must be, otherwise it won't balance. If there is a force upwards, if we think about it, if there is a force downwards from both of these sides for the whole thing to be in equilibrium, there must be a force upwards from here. So I'm going to call that FB. Okay. So if that's the case, then what we're going to do here is we're going to apply these different forces. We're going to sort of work out what these forces are. So let's pick some reasonable values. Well, you've got a diving board. I reckon you've probably got about 4 meters there and maybe 1 meter there, let's say. Now, we want to work out what these two forces are. So if we want to work out FA, first of all, what we do is we take the moments about support B. Okay, so we assume we want to work out the moments about there. So if that's the case, we know that FA, well, the clockwise moment, sorry, I'm skipping a step. The clockwise moment must equal the anti-clockwise moment. Okay, so if I take the clockwise moment, that's going to be from the diver about to jump off, 500 newtons multiplied by 4 meters. Is equal to the anti-clockwise moment, which is the force A, trying to turn it all that way, force A multiplied by the perpendicular distance of 1 meter. So what happens is I know that the force A is going to be 2,000 newtons, and it will be by definition downwards. So that gives you your first force. Now, the other way to work out the force upwards from B, FB, there are two ways of doing this, and they should come up with the same answer. So I'm going to do both just to show you that they do. The first one is using linear equilibrium. There's a total force downwards on this plank, a force downwards of 500 newtons and a force downwards of 2,000 newtons. So the total force downwards is going to be 2,500 newtons. Okay, so if that's the force downwards, there must be an equal and opposite force upwards. And the only upwards force on here is from support B. So because that's the only upwards force, that FB must be 2,500 newtons. The other way to do it is to work from scratch and actually take the moments about A. All I'm really doing is I'm showing you that the physics here does work. It does actually agree. So if I take the moments about A, my clockwise moment is produced by the diver. Now he's got a force of 500 newtons, but now we're looking at the distance from A. So that's 4 meters plus 1, so that's 5 meters. So that's going to be 5 meters multiplied by 500 newtons is equal to the force from B, the anti-clockwise moment, which is caused by the force from B, multiplied by the distance between A and B, which is 1 meter. So it turns out the force B is 5 times 500, which is 2,500 newtons. Okay, so that is one particular example of using moments. So all you really do, if you've got two supports, is you take one of the supports to be a pivot, and then you work out the moments caused by the forces involved and the forces on the pivots. Okay, so that's one particular sort of more complex example. Some people seem to find that quite a difficult one. You also have to think about the centre of mass. The centre of mass, remember, is the point at which all the mass of an object can be said to act. It is the same place as the centre of gravity, which is the point at which all the weight of an object can be said to act. They're actually pretty similar things. In terms of where they are in a uniform object, it's pretty much the same. So if I wanted to find the centre of mass of this rectangle, my centre of mass is actually the geometric, is the geometric centre. Can be found by just drawing from corner to corner. So the centre of mass is right in the middle here. Okay, so that gives you the centre of mass. Now, you could do all kinds of interesting things here. If you wanted to tip something over, so let's say this is on a surface represented by the ruler. If I tipped this over slightly and I drew a line directly down from the centre of mass, the vertical line from the centre of mass, you notice that the centre of gravity, that line down from the centre of gravity, is on this side of the pivot. So this has become a pivot. So what would happen is that this block would then just fall back to where it was. If I tilted the block further, then my vertical line downwards from my centre of gravity is now on this side of the pivot, so the block would fall over. So that's why things that are short and wide have greater stability. The stability basically means that it returns to where it was when you let it go. So you could do all kinds of different calculations. Now, a lot of people get very, very sort of confused by some of these calculations, but actually there is nothing magical about it. Imagine this block of wood. This is a block of wood, and it has a weight of, well, let's say 4 newtons. Okay, and let's say that it is 10 centimeters, well, yes, 20 centimeters wide and 50 centimeters tall. Okay. Now, you'd want to know how much force is required to tip it over. It sounds like a really difficult question, but it's actually not. You're just using moments. So if we tip this over, this corner here would become a pivot. Now, whenever I'm doing a moments question, and the same went from when I was a sixth form, from when I was your age, I always drew with a little black triangle where the pivot was. It makes life a lot easier. Well, if this is a uniform block of wood, if this is a uniform block, we could work out, first of all, the moment caused by its weight. Well, all its weight acts about the center of mass, or so center of gravity. So the weight of the object, the weight of it, is given by that arrow. Now, if it's uniform, then we know that that distance is going to be 0.1 meters. If it's a uniform material, okay, it'll be in the middle. The center of gravity will be in the middle. And that's going to be 4 newtons, the weight of the block, the weight of the piece of wood. Now, if I wanted to push that, I would need to overcome the moment created by this weight, about this pivot. So if I think about it carefully, if I think about it very carefully, what I can do is I can start to think it through. Well, we've got here an anti-clockwise moment. If it wasn't for the rest of this sort of bench top, if this was just a pivot, then this whole thing would rotate anti-clockwise in the opposite direction to the hands on a clock. So if it did that, then it has an anti-clockwise moment. So the anti-clockwise moment is equal to the force times the perpendicular distance. Well, this is the perpendicular distance between the force and the line of between the line of action of the force and the pivot. So that's going to be force, which is 4 multiplied by 0.1. The clockwise moment would be, if there was nothing else here, if there was just the pivot and this force, it would try and turn the whole thing clockwise. So if this tries to turn it clockwise, then it's the force multiplied by the perpendicular distance between the line of action of the force and the pivot. In other words, this distance here, 0.5 meters. So we know that for equilibrium, the clockwise moment equals the anti-clockwise moment. So the clockwise moment is force times 0.5, which is equal to 4 times 0.1. So the force is 4 times 0.1 over 0.5, which is 0.8 newtons. Okay, so in other words, that would need to be subject to a force of 0.8 newtons from the top here in order for this block to tip over. And just to prove the point about having a lower center of gravity means that an object can be more stable, if I then took the same block, okay, but I turned it on its side, we know the center of mass is in the center of gravity, and therefore center of mass is in the middle. I'm not going to use working lines here. And we know it's on a bench, on a tabletop or something like that. So we take a similar position pivot. Well, that's going to be 0.5. And that's going to be 0.2. So we're going to apply a similar force and call it F dashed. And we could actually do the same sort of sums. Well, we know the center of mass will be acting, center of gravity will act about this point here. Still the same block, so it's still 4 newtons. So we can work out straight away this perpendicular distance between the line of action of the force and the pivot is going to be 0.25. So we know that the anti-clockwise moment is going to be equal to, well, the anti-clockwise moment is going to be the force F. So it's going to be the 4 Newton force. multiplied by 0.25. Okay. And the clockwise moment is going to be this force F multiplied by 0.2. So the clockwise moment equals the anti-clockwise moment. So 4 times 0.25, well, that's just 1. F times 0.2 F there. So F is going to be 1 over 0.2, which is equal to 5 newtons, which is much greater than it was in the first situation, which goes to show that having a wide base and a low center of gravity increases stability. In other words, it's harder to actually push this block over to such an extent that it doesn't return to where it came from. The rest of the situations with moments are all about being able to identify them. So you could get all kinds of situations. There's sort of the most common one that's difficult, I think, that people find very difficult, are to do with bridges. So if you had a bridge with 2 supports, okay, imagine there's a river in between the 2, okay, and you want to work out the 2 upward forces. Let's imagine the bridge is 10 meters long, just for fun. And let's imagine you've got some object. Let's put him over here. Got some object here with a weight of maybe 100 newtons, let's say. Okay. And you know that there's going to be, you want to work out the forces here. The weight of the bridge, let's say, is 50 newtons. Now, the weight of the bridge is always going to act on the center of gravity. That's the point at which all the weight is said to act, which is going to be about halfway along. I personally find it easier if I measure. Put my center of mass there, center of gravity there. So let's say it was 50 newtons, just for fun. That's 10 meters, 50 newtons. So you can start doing your sums straight away. You can work out straight away that this distance is going to be half of the way along. So a half of 10 is going to be 5 meters. It's 5 meters from there and 5 meters from there. This distance, well, you'd be given it in the question. You'd be told that maybe that's going to be 2 meters. Okay. So how do we go about finding out the forces? Well, we pick one as being the pivot, and it doesn't matter at all which one you pick. So I'm going to take FB, okay? Just the important bit is to say what you're taking the moments about. So the moments about FB, okay? So if I take the moments about FB, got my clockwise moment coming from FA, times 10 equals the anti-clockwise moment, which is from this force downwards and this force downwards. So if that's 10, that's 5, that's going to be 5 as well. So that's going to be 5 times 50, 5 meters times by 50 newtons, plus 100 newtons multiplied by 2. So force due to A is going to be 5 times 50 is 250 plus 200 over 10. So that's 450 divided by 10. So that's 45 newtons, let's say. Okay. Then you just take your linear equilibrium to work out the force. That's from force A. So that's going to apply 45 newtons. Then you just take your linear approach. So you've got 50 plus 100 makes 150. That's the total force downwards. So to get the total force upwards, that's going to be 150 minus the 45. So we show our working. 150 minus the 45 gives you 105 newtons. That's how you go about answering moments questions. The key is really to look at what's providing the clockwise and anti-clockwise moments. I think from the attempts that I've seen, most people have the right ideas, but I think there is a need for a bit more practice. Okay, right. Does anybody have any questions? We have 15 minutes. And I think we should, well, we've got 14 minutes, I should say, and I think we should make use of it. So does anybody have any questions?
Yeah, I have one, Gary,
Yeah,
but it's not about like any exercises.
that's right.
It's about like the people who are like out of the school.
Yeah.
They are going to do like on computer. How is it gonna work like that?
Well, what will happen is as soon as I've got the full list together, unfortunately, one or two people who are supposed to apply for their UFP exams have been very slow about doing so. What I'm going to do is I'm going to send out the papers. I'm going to send out instructions in about probably a couple of days' time. I'm going to send out instructions on how to access the exams at home and what to do in terms of setting up a suitable exam space, that sort of thing. What will happen is you'll be sent the exams on the day. You'll have to sign a declaration to prove that you are using proper exam conditions, that you're not using books or anything. You have to sign a declaration which confirms that, which means that if you do then cheat, you are in breach of contract. Makes it a lot easier for me to nullify marks if I have to. I've never had to do that because most people are honest. I think what could also then what also then needs to happen is you'll get the exam paper on the day of the exam, and you'll have sort of a 24-hour window to do the paper. Scan it on your phone using a document scanner. Again, the instructions I've got they tell you, it tells you how you can use a document scanner on your mobile phone if you need to, and then resubmit the work in the same way that you'd submit a homework on Satchel. So that's how it will happen if you're working remotely. However, if you're in school, the current plan is if schools are reopened, that you will go to an exam room and you will take the exam in the exam room. There may be alternative arrangements if we're still not allowed to use that. Okay.
Okay, thank you, Gary.
Okay. Any questions? Anything else? No? Does anybody want to talk about a topic that maybe they'd like me to line up for next week so that we're not spending our entire time just doing practice papers? Are there any topics that anybody wants me to have another look at and show you?
Gary?
Yeah.
Uncertainties.
Uncertainties. What do you mean? Is it combining them or?
Yeah, combining them.
So I mean,
uncertainty.
I can clear that up. If you've got, say, x equals y z squared plus g, let's say we've got something like that. Looks like a nightmare, but let's imagine that y is 2 plus or minus 1, z is 4 plus or minus let's say 1 as well, and g is 20 plus or minus 5, let's say. If I wanted to work out what x was, obviously you can work out what x is first of all. That's trivial because that's y, which is 2 times z squared, which is 4. So 4 squared is 16, 18 plus 20 is 38. So x comes out to be 38, okay? Now, that's the easy bit. There's working out the uncertainty. Well, what we've got here, we've got two factors. They're multiplied together. When they're multiplied or divided...
Sorry, I don't think x is 38.
Sorry?
I don't think x is 38.
Okay, I might have got it wrong. Let's have a look. So x is y, which is 2. Absolutely, that's right, because it's not 2 plus, it's 2 times, isn't it? 16, 16, 32. So that's going to be 52. Sorry about that. Slight senior moment. Okay, I think that's right. So 2 Z squared is 16 times 2 is 32. 32 plus 20 is 52. Right. Now, there are a couple of ways of doing it. Now, the first way, pretty simple. First way is, I'm just going to do them both so you can see that they both work and they both give you roughly the same result. The first way is to look at the percentage uncertainty. So you've got the percentage uncertainty in Y. So that's the uncertainty in Y over Y. It's going to be 2 plus or minus 1. So that's 1 over 2, which is 0.5. The percentage uncertainty in Z is, well, the uncertainty is 1, Z is 4, so it's 1 over 4, which is 0.25. These are obviously big uncertainties. And the percentage, well, that's all we need to start off with. So to work out the percentage uncertainty of that part of the expression, all we've got to do is add them. So you've got Y times Z times Z. So it's Y, the uncertainty in Y plus the percentage uncertainty in Z plus the percentage uncertainty in Z. So the percentage uncertainty in YZ squared is going to be 0.5 plus 2 times 0.25, okay? Which comes out to be 1, which is 100% uncertainty, which is pretty awful. Okay, so now that's, you've got the uncertainty, the percentage uncertainty in there as being 100. The uncertainty in YZ squared is going to be 1 times whatever YZ squared was. Well, YZ squared was 2 times 16, which is 32. Okay, so if one of them work out, if you've got two factors being added together, you just add their absolute uncertainties together. So the absolute uncertainty in YZ is 32. The absolute uncertainty in G is 5. So it's 32 plus 5 gives you 37. So in other words, the uncertainty in X is going to be plus or minus 37. So if I said that X was going to be 52 plus or minus 37. Okay, which is quite a high uncertainty, but then that sometimes happens in science. Now, the other way to do this is to use bounds. So I could work out the upper bound and lower bound. So the upper bound for this expression would be, well, these would all be, because there's no divided term in here, these are all going to be the highest possible numbers. So if Y is 2 plus or minus 1, then the highest it could be is 3. If Z is 4 plus or minus 1, then the highest it could be is 5, and I've got to square it. Then if G is plus or minus 20 plus or minus 5, then the highest it could be is 25. So if I say 3 times 25, which is 75, because 5 squared is 75, so 3 times 25 is 75, plus 25, it's 100. Okay? The lower bound is the lowest this expression could possibly be. So here, Y is 2 plus or minus 1. Well, the lowest that can be is 1. Z is 4 plus or minus 1. So the lowest Z could be is 3. And it's squared, don't forget. Plus the lowest that this G could possibly be, G is 20 plus or minus 5. So the lowest it could be is 15. So 1 times 3 squared is 9. 9 plus 15, that's going to give me 24. Okay. Then, just like you do with working out the uncertainty in a measurement, it's the range over 2. So the range is the upper value minus the lower value over 2. Well, 100 minus 24 is 76. 76 over 2 is 38. Okay, So in other words, my X value was 52 as it was before, plus or minus 38, which is pretty much the same. You can see that both of those are good estimates. Sorry, there. Both those are good estimates of the uncertainty in a value. Okay. The only time it gets complicated is if you have to use division or subtraction. So let's imagine we have W equals X squared over Y. So imagine X was 5 plus or minus 1. Y was, say, 2 plus or minus 0.5. Again, we could use the traditional mathematical algebraic way of working out the percentage uncertainties. The uncertainty in W, percentage uncertainty in W is the percentage uncertainty in X squared. So it's 2 times the uncertainty in X over X plus, because we're still adding, because even though we're dividing the factors, percentage uncertainty in Y over Y. So the percentage uncertainty in X is going to be 1 over 5, which is 0.2, times 2 is 0.4. Percentage uncertainty in Y is going to be 0.5 over 2, which is 0.25. So in other words, it's 0.65, 65%. So the uncertainty in W is going to be the uncertainty in W is going to be 65% of whatever W is. So W, well, let's work it out quickly. X squared is 5 squared is 25, divided by 2 is 12.5. Whoops. So W is equal to 12.5, okay? So the uncertainty in W is 0.65 times 12.5.
Period 4 ends.
Gives me 8.125. Well, I'd say probably 8.1. That's probably about as good an uncertainty as I should really try and do here. So W is equal to 12.5 plus or minus 8.1. Okay, it's reasonable, quite a high uncertainty. And the same thing happens if we do upper and lower bounds. The only difference here is to get the upper bound, we're looking at the lowest value of Y and the highest value of X. So the highest value X could be 6. So 6 squared is 6 is a 36 over the lowest value that Y could be, which would be 1.5, which is 24. That's the upper bound. And the lower bound is the lowest value that X could be. So that's 5 plus or minus 1, so that's 4. 4 squared is 16, divided by the highest value that X could be, which would be 2.5, which is 6.4. Okay, so to get the uncertainty, I would just take the range over 2. So it's 24 minus 6.4 over 2, which is 8.8. So my other estimate for the uncertainty is W is 12.5 plus or minus 8.8. And again, pretty much similar. So either method is absolutely fine. Remember, in physics, I'm not judging you on whether or not you do it my way. I'm judging on whether or not you do it correctly. Oops, what's happened to my camera? Oh dear. I think I'll have to end there. My camera's just decided to. There we go. I'm not judging on whether or not you do it my way. I'm judging on whether or not you do it correctly. Okay. So do use either method when you're trying to combine uncertainties. Right. Tomorrow you will have another practice paper to do. Please, 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 please. What I'd like you to do is practice doing the questions as best as you possibly can. So I just want to keep on getting that strong development. So have a go at the next paper that I'm going to give you tomorrow, and that will be due in, please, on Monday at the latest, please. If I don't receive decent attempts in, doesn't have to be perfect, just has to be the best you can do. If I don't receive an honest effort on the by Monday morning, I'll be writing home to parents, because I think it's going to start getting to the stage where I'm going to start worrying. Okay, I will see you all. Well, I'll be logged in tomorrow morning, so I'm going to stay on Zoom tomorrow morning. I'll put a Zoom link in so that if you want to sort of stop and ask me anything, you can do so. Okay, I'll see you all either tomorrow or on Tuesday, depends on whether or not you log in.